In this lecture, I'm going to introduce non-dimensionalization or de-dimensionalization of integrals. Dimensional analysis may give us the option to obtain some information about integrals instead of direct integration. We may use dimensional analysis to transform the integral into a simpler form, where we obtain some information about the functional dependence of the integral on the dimensional quantities. While we are doing a calculation in physics, we may encounter integrals or differential equations. Generally, the integrand may have dimensions. For example, in statistical mechanics, when we use Maxwell-Boltzman distribution to calculate moments, averages, we should integrate over some functions. When we are going to obtain the surface area or volume of an object or moment of inertia, we need to calculate some integral. Let's consider first the Maxwell-Boltzman distribution, the velocity distribution function for some non-interacting particles of mass m at temperature T is proportional to where k is the Boltzmann constant. Velocity distribution function for the x direction is the fraction of particle whose x component velocity are between vx and vx plus dvx. With the normalization property. In this equation, the right-hand side is dimensionless, so the left-hand side should be also dimensionless. Then the dimension of, but exponential is dimensionless. Then C1 should have dimension U inverse, or normalization property can be written in this form. This integral is a function of m, k, and t. This means that C1 has the dimension of inverse of velocity, and f is the dimension of velocity due to this term which has dimension of velocity. Then we should construct with the quantities m, k, and t a velocity. It can be easily seen that velocity should be, the characteristic velocity is kt over m. Then C1 should be proportional to U inverse, which is m over kt. We can obtain the value of the function f using the integral in this way. F is equal to, we can non-dimensionalize this integral. In fact, by defining v tilde as, then f is, this is a dimensionless constant, so f is proportional to u, which is equal to kt over m. For the three-dimensional case, the distribution is where C3 is, it's proportional to. If we directly calculate these constants, C1 is equal to 2 pi kt over m, and C3 is 2 pi kt over m to the power 3 over 2. We can obtain moments, for example, the averages, average of energy, for example. E is equal to, which is, this term is equal to, by replacing the distribution, velocity distribution function, this is we can non-dimensionalize this integral by defining then the average is, this is a dimensionless constant, and the result is proportional to, then we obtain the direct calculations gives, and the average energy is. As another example, let's consider the surface area. For example, we know, or we can easily obtain the surface area of a circle. It is the double line integral over x and y, where the boundary is given by, this integral is, we can de-dimensionalize this integral by defining, then this is whose boundary is given by, dimensional analysis does not give this integral. By direct calculation we can obtain that this integral is equal to pi. But for example, for an ellipse, the integral is dx dy, whose boundary is, by non-dimensionalizing this integral with these equations, we obtain, but this integral is a non-dimensionless constant which is equal to pi. So the surface of an ellipse is pi AB. In the same way, we can obtain the volume of an ellipsoid using the volume of a sphere. Volume of a sphere is 4/3 pi r to the power 3, and volume of an ellipsoid can be obtained using the similar argument as the surface. It can be seen that we can obtain a moment of an inertia, for example, of a disk in the form of an ellipse, A and P. If we know the moment of inertia of a circle of radius r, we can obtain the moment of inertia of an ellipse with the semi-axis A and B. The moment of inertia for this shape, a disk of radius r and mass m, it's equal to, and exactly with the same arguments as we did for the previous parts, it can be shown that the moment of inertia with respect to the axis z, which is orthogonal to the ellipse surface, it's equal to, as the final example, let's consider the period of oscillation of a harmonic oscillator and a non-harmonic oscillator. For harmonic oscillator, the energy is kinetic energy plus potential energy, where A is the amplitude of the oscillation. From here, we can obtain x dot is equal to, x dot can be both positive and negative for the motion in this direction or in this direction. Then period of oscillation t is equal 4 times, which is, we can non-dimensionalize this integral using this definition. Then t is equal, this is a dimensionless constant, then the period of oscillation is proportional to m over k, and it doesn't depend on the amplitude for harmonic oscillator. The direct calculation gives the constant of proportionality to be 2 pi. For a non-harmonic oscillator, when potential is, for example, in this form, 1 over 2 alpha x to the power 4, you can show that the period of oscillation is proportional to 1 over a square root of m over alpha. For this case, the period of oscillation depends on the amplitude.